So when we first started talking about work and energy, we talked about the idea that forces can do work on objects as they move, and if your force is constant, then we can calculate that out by taking the magnitude of the force times the magnitude of the displacement the object moves through times the cosine of the angle between those two vectors. And so we said that if you've got a situation like this where there's a force that pushes some box across the surface, that box moves through some displacement, then you can take those two vectors, draw them both from the same origin. That will let you see that angle that you need for the cosine term, and then you can go ahead and calculate out the work done by that force. Well, we can also talk about the work done by forces as they act on objects that rotate. And so part of what we're going to do is we're going to introduce this idea of torque. Now in the next module, we'll come back and be much more explicit about the definition of torque and what we're going to do to calculate it. So sort of at the moment, mostly what we're doing is just kind of introducing it as a conceptual idea. But the idea is that forces can act on extended objects that causes them to rotate, and that the way they do that is by exerting a torque. And so what we're going to use to denote the torque is a lowercase Greek tau. And so that's what this looks like. It looks like sort of a weirdly written T. It's close enough. That's a tau. That's our symbol for torque. And so what we've done again is we've replaced our translational quantities, force, displacement, with angular quantities. And so part of what you see is that the torque is going to play the role for rotational stuff that force tends to play for translational stuff. And then again, instead of a translational displacement, we have an angular displacement. So you can calculate the work done by a constant torque on an object as it rotates by taking the magnitude of the torque times the magnitude of the angular displacement times the cosine of the angle between them. What we're going to do with this class is we're going to focus on torques and angular displacements that always lie along the axis of rotation. And so what that means is they're either going to line up, so either the torque and the angular displacement are going to point in the same direction, and therefore phi is 0 and cosine of phi is positive 1, or they're going to point in opposite directions about that axis, and so the angle between them is 180 and the cosine of 180 degrees is negative 1. So we're going to sort of limit thinking about the work done by torques on things that rotate as magnitude of the torque times magnitude of the angular displacement times plus or minus 1 based on whether or not that torque does positive work or negative work. So as sort of an example to kind of start to put a picture into your head about how this works. So let's say I have a disk. That disk can rotate about its center, and then I'll let a force act on the outside of this disk. That this force acting on this disk is going to try and make it spin counterclockwise. So you can think of this as the torque that this force generates is going to point, if it's trying to make the disk spin counterclockwise, it's going to point out of the page. If this disk is rotating counterclockwise, then of course if I take the fingers of my right hand and curl them clockwise, my thumb points out, and so I can see here that the angular displacement also points out of the page. So this is a situation where the torque generated by this force and the angular displacement point in the same direction. The angle between them is 0, the cosine of that angle is positive 1, and so this is a situation where the force generates a torque which does positive work. That positive work goes towards increasing the rotational kinetic energy of the disk. So this force would do positive work to help the disk spin faster as it rotates counterclockwise. Well, let's let the disk continue to rotate counterclockwise, but now let's change the force. And so instead of pointing down, let's let it point to the right, and so now it's acting on the top edge of the disk, acting at the right. If you were to push the disk with this force, you can sort of intuitively see that that's going to try and make the disk spin clockwise rather than counterclockwise. So this force acting at this point on the disk is going to generate a torque that makes the disk spin clockwise, which means that torque will actually point into the page. If the disk is spinning counterclockwise, that angular displacement points out of the page. So this is a situation where the torque generated by this force points in the opposite direction as the angular displacement. The angle between them is 180 degrees. The cosine of 180 degrees is -1. So here's a situation where the force generates a torque which does negative work. That negative work goes towards decreasing the rotational kinetic energy of the disk. Okay? So in the same way that we had forces that could do positive or negative work on objects as they underwent translational motion, we'll have forces that generate torques. Those torques can do positive or negative work to change the rotational kinetic energy. The other detail that we want to go ahead and talk about when we're talking about work being done on rotating objects is the work done by gravity. And what we need to emphasize is the gravitational force only does work on the center of mass of an object. And so when we were dealing with a situation like this, where we said, hey, let's take a massless string, its length is L, let's take some mass, attach it to the end of that string, we'll hold it out perpendicular, we'll release it from rest, and that mass will swing down. And so we're interested in figuring out how fast the mass is moving when it gets down here at the bottom. One way to do that, of course, is to think about conservation of energy. We can think about the translational kinetic energy of the mass. So again, it's moving. So we're going to keep track of the translational kinetic energy in terms of 1/2 mv squared. And we can keep track of the gravitational potential energy. And again, because all the mass was located down here, right, so we were effectively treating this as a point particle, we can pick where the mass ends up when it's vertical, when the string is vertical, let that be the 0 point for the gravitational potential energy, and then where it starts was this full length of the string back up here in terms of calculating the initial gravitational potential energy. We release the mass from rest. Its gravitational potential energy at that point was mg times the full length of the string, plus there weren't any non-conservative forces doing any work, so that term is 0, equals the final kinetic energy of the mass plus it's at the 0 point for gravitational potential energy. So what happens if we take that mass and instead of having it stuck at the end of the string, we spread it out over an entire rod? So now we have a uniform long thin rod with that same length L. And so of course the center of mass of the rod sits right here at its middle. So if this is a uniformly distributed rod, then the center of mass of the rod is right here at the center of the rod. So again, we're going to hold it out horizontally. We're going to release the rod. It's going to swing down. And so we're interested in what's going on when the rod reaches as it's swinging through the vertical. Again, we're going to use conservation of energy to think about this, but there's two changes we're going to make. The first is we're actually going to treat the motion of the rod as entirely rotational kinetic energy. It's just rotational kinetic energy about this pivot point. So we'll need to use the parallel axis theorem to calculate out what I is, because it's not rotating about its center, it's rotating about this point at its end. The other detail, of course, is that the work done by gravity as this rod swings down is tied up in these gravitational potential energy terms. And so, of course, if gravity only does work on the center of mass, then I'm only interested in where the center of mass is located at the end. So instead of having the gravitational potential energy equals 0 down here at the bottom of the rod, I want to place it right here where the center of mass is. So now my 0 point for the gravitational potential energy is at the center of the rod, which means that this height that it started at initially is now half the length of the rod, not its full length. So when I go ahead and plug all that into my conservation of energy equation, I still have an initial kinetic energy of 0. My gravitational potential energy now reflects the fact that the gravitational force is only doing work on the center of mass, because the center of mass only moved down by a distance of L over 2, half the length of the rod. again, we'll assume that this is a frictionless pivot, so there's no work done by non-conservative forces here, equals, again, I'm going to deal with my kinetic energy in terms of rotational motion. The center of mass of the rod ends up at the gravitational zero point. So it's just one detail that we need to make sure that we keep track of now that we have these extended objects, is that when you're thinking about the work done by gravity, that's going to go into these potential energy terms, right? The potential energy, how the potential energy changes is related to the work that's being done by the gravitational force. We need to keep in mind that gravity only works on the center of mass, so that's the point that we're interested in thinking about.